Welcome back to the series of lectures on high-performance scientific computing. As we are coming close to the end of this course, we will now be reviewing the important material that was covered in this course. In this video, we will review OpenMP. What is OpenMP? OpenMP or Open Multiprocessing is an API for parallel programming which is compatible with C, C++, and Fortran. What it really achieves is simple directive-based parallelism. OpenMP, more importantly, works on the shared memory model or shared memory machines, where you have multiple CPU cores which are attached on the same motherboard and have access to the same global memory. This is widely used for multi-threading on CPUs. Today, you have a lot of multi-core CPUs because of different hardware engineering reasons. An average desktop computer today has at least 4, if not 8 CPU cores. On the servers, you can go up to as high as 256 CPU cores on a single node. So it is very important to harness the entire power of all these cores by writing multi-threaded programs. And OpenMP gives you a simple way to parallelize it using multiple threads. The other good advantage of OpenMP is that it is portable and scalable across different architectures as long as there are compilers which have OpenMP implementations. So why do we want to use OpenMP? We had discussed the fact that most research groups will have some essential serial code which has been there as legacy for many years doing some amount of science. And you would like to sort of speed up the serial code and extract the maximum performance out of the multi-core CPUs that are present. A directive-based parallelization technique like OpenMP is easy to integrate with existing serial code. You need to have very few code modifications because all you need to introduce is the directives. You can easily switch between the serial and parallel versions of the code. Especially, this is important if you want to debug the program to see if the output is the same when you're doing the calculation in serial or when you're doing the calculation in parallel. It gives you a higher level of abstraction for parallelism where the programmer can then focus on the algorithm and the science. And OpenMP is extremely optimized for multi-core systems. So what is the OpenMP execution model? So remember, it was the fork join parallelism. So there essentially you have a master thread which spawns a team of worker threads. Now these threads execute in parallel and these threads have no specific preference in relation to each other. At the end of the parallel region, the worker threads terminate, leaving only the master threads. So every time, based on the directive, an OpenMP region is reached, the master thread will create a lot of worker threads. Threads will then work on this data. And then at the end of the parallel region, the worker threads will be terminated and leaving only the master thread. So this is both a sort of an implicit and explicit parallelization model. How do we enable OpenMP for codes? First of all, we have to use the directives at the appropriate places. And when we compile this code for OpenMP support, we need to put the appropriate compilation flags. For example, in GCC, you would use a flag called fopenmp. The same for CLang. For the Intel compiler, you would use qopenmp. If you're going to call some specific OpenMP related functions, then you will have to include the header file omp.h so that the references to the functions are available. What happens if you do not use these compilation flags? So then the OpenMP directives which are there in the code are merely regarded as comments and disregarded in the final program output. So essentially the code will then behave as a serial code. So this gives an easy switch between going from the parallel version of the code to the serial version of the code and vice versa. Extremely useful for debugging the program or the algorithm. So what are the different OpenMP directives that we covered? We had talked about the hash pragma OMP parallel, which defines a parallel region. Remember that this hash pragma is the C version of it. In Fortran, the semantics would be slightly different. In this review session, we'll be covering only the C versions of the directives. So you have hash pragma OMP parallel, which defines a parallel region. You have hash pragma OMP for, which distributes loop iterations. So for example, if you have a for loop, different parts of or different indices of the for loop will be taken up by different threads. Hash pragma OMP sections executes independent code in blocks in parallel. This could be different sections of the code or different bits of code. It's not a loop which is being divided. In a loop, it is the same operation. It's just that the operands or the data members on which the loop is operating are different. Here in sections, you can actually execute different functions, completely different code in parallel by different threads. If you use the directive hash pragma OMP single, it ensures that only one thread runs that particular part of the code. If you use hash pragma OMP master, only the master thread will execute. And finally, because there are different threads running, and typically they all run at different speeds, and there is some sort of asynchronicity between the running of the threads, because finally the threads are being scheduled by the operating system on the different CPU cores. So it's quite possible that an asynchronicity develops, or if you use sections where they're essentially threads are running different bits of code, asynchronousness normally develops or naturally develops. We have to synchronize the codes at some point of time. And for that, we use the hash pragma OMP barrier, which is sort of the synchronization point for all threads, or sort of the waiting point for all threads. In the sense, if you put an OMP barrier in your code, all the threads will come and wait there until every other thread has finished its task. So how does a parallel region work? So the basic parallel construct is you identify a parallel region and within the curly braces, and you say OMP parallel. So each thread in this case will execute the printf separately and it will output its thread num. So the function OMP get thread num retrieves the thread ID. The function OMP get num threads returns the total number of threads that are in action at any given point of time. How do we control the number of threads? By default, it uses all available cores. You can explicitly set, for example, if you are on a 24 core machine, but you just want to use 4 cores, then you will say OMP set num threads 4. You can also set this variable outside the program in the environment by doing export OMP num threads equal to 4. At runtime, you can figure out how many threads are there or maximum number of threads by using the OMP get max threads function. Remember, you can also declare the number of threads to be greater than the number of cores. But in that case, you will invariably end up with a slowdown because then the processor will start scheduling the threads appropriately. For example, on a 4-core machine, if you set the number of threads to 8, at any given point of time, only 4 threads will be executing as the operating system will schedule those 4 threads on the 4 cores and the other 4 threads will be waiting. And the 4 threads will then be swapped in and swapped out based on the operating system's requirements. Because of the excess management, this usually will result in a slowdown. So it is always advisable to use at max the total number of cores as the number of threads or fewer than that. Then how do we have the work sharing constructs? The hash pragma OMP for divides loop iterations among threads. For example, if you have 4 threads and you have a loop which the index goes from 1 to 100, the threads will then divide the loop based on the 100 iterations it needs to do. Each thread will be given 25 members. The OMP sections, as we talked earlier, assigns different tasks to different threads. So for example, in one section, you can call a function to generate a random number. In the other section, you can calculate a function to calculate the value of pi. In the third section, you can calculate a factorial, so on and so forth. The task is immaterial. You can assign different tasks to different threads. As we said earlier, OMP single ensures that only one block of code runs only one thread. This is very useful if you're doing something like file writes where only one thread needs to write to a single file. And master ensures that the execution is done only by the master thread, in the sense that only one person, the identified person, will accumulate all the information and then work on that. The difference between single and master is the fact that single could be any thread, master is always one thread, which is thread 0. So this is the example for loop level parallelism, where we have a parallel for loop, and here we are doing AI is equal to BI plus CI for all the indices from 0 to 99. Here the compiler will distribute the iterations across the available threads. Obviously, the performance that you gain depends on the loop iteration count and the workload. This is a very simple thread, has very little workload, so you might not see too much performance improvement. Also, the number of threads will matter. Let us say that if we take 2 threads, then you will go from 0 to 49 in one thread and 50 to 99 in the other one. If it is 4, you will do 25 threads. Remember our old friend Amdahl's law, because there's some management we need to do for thread creation and thread destruction. If we use, say, 25 threads over here, then usually the performance is really bad, because the management of 25 threads becomes harder. The other important thing is synchronization. So especially when you want to update a single variable and multiple threads are accessing that particular variable, we need to ensure that these variables are updated in a synchronized manner, otherwise you'll end up with wrong results. And one way of doing it is something called as critical sections. So if you mark a section to be critical, that means all threads will work on it, but at any given point of time, only one thread will work on it. During that period when that one thread is working on it, all the other threads will be waiting for their turn, and nothing will really happen in parallel. So essentially, this part of the code becomes effectively serial, because each, in this case, for example, we are updating the value of sum with the value x, and we are doing it critically. So that means at any given point of time, only one thread is able to write to the variable sum, and all the other threads will be waiting. So effectively, the process has become serial. This will definitely increase the slowdown of the code, but sometimes these are unavoidable because we need to do such calculations. Another way to do the same thing is to use the atomic function. The atomic function basically applies to the next line of code. Here, sum is again being updated atomically, only one thread at a time. In the critical section, you could add multiple lines of code, whereas an atomic operation is just for that next line. Barriers. We know that different threads will run at different speeds based on the input data that they're getting, based on the CPU assignment or the core assignment, how the operating system handles it, based on the function they're actually calculating if you're doing sections parallelism. And if you want all the threads to synchronize at one point before moving forward, you have to use the OMP barrier. The other thing is ordered regions, maintaining loop execution order. Remember, there's no particular preference to the loop execution when we're doing a parallel for, but if you want some ordering to be done, then we use the OMP ordered function. The other thing that is critical in OpenMP is data sharing. We have shared variables which are visible to all threads. You have private variables where you have a separate copy for each thread. You have first private, which is initialized in the master thread's value, and then it becomes private. And finally, you have last private, which is the copy of the last iteration's value to the master thread. And you have to declare different variables to be either shared, private, first private, or last private using the example of the hash primer given. Another key bit is the scheduling strategy, how the threads are being scheduled. One way of doing things is static scheduling, where a predefined chunk is being assigned, for example, in for loops. You can also do dynamic scheduling, where threads request chunks at runtime. We can also guide the scheduling by looking at chunks of data which decrease in size over iterations. For example, we discussed how to do schedule dynamic for. Finally, a lot of OpenMP operations require reductions, which is essentially doing aggregates in values across different threads. These reduction operations could be several. It could be doing a sum, it could be doing a product, it could be doing a minima, it could be doing a maxima, it could be doing logical ands, logical ors, so on and so forth. Here is an example where we are doing the reduction in the value of the variable sum. We are looping through an entire array AI, and we are summing it up into a single variable sum, which is a critical operation. Now, when we do a hash pragma OMP parallel for and put the reduction operation plus equal to sum, each of the threads will now initially have their own private copy of sum, will compute the local sum, and then it will compute the global sum at the end of the parallel section. The supported operators which are available in reductions are, as I said, addition, multiplication, min max, logical AND, logical OR, so on and so forth. So we looked at a few case studies. One of the most important case studies that we looked at was parallel matrix multiplication, where we used OpenMP to accelerate matrix-matrix multiplication. We used the for loop parallelization construct, and then we also collapsed the innermost two loops. We also improved the performance through parallelization of the outermost loops. Remember, the outermost loops run the fastest or the slowest and span larger bits of memory. So it's better to optimize at the, or rather parallelize at the outermost loop levels. The performance improvement is gained through parallelizing the outer loops. If we had moved the hash pragma OMP parallel for inside, our performance would have been bad. The other case studies that we talked about was image processing for doing image convolution, where we looked at parallelized filter operation across pixels. For example, edge detection, blurring, so on and so forth. And this gives a significant speed up because this is almost an embarrassingly parallel problem. We also looked at OpenMP in scientific computing, where we looked at computational fluid dynamics problems, especially the problem of doing the Laplace's equation. And that's sort of the basic building block for doing climate modeling applications and parallelizing physics calculations. So in summary, OpenMP enables easy multi-threading. It uses parallel regions, work sharing, synchronization, and reductions efficiently. It optimizes scheduling and minimizes synchronization overhead. It's an easy foray into parallelizing on multi-core CPUs. Thank you.